Imagine we have some vector phi, and we also have the representation of phi in some orthonormal basis E with vectors E1, E2, etc., En, and the components alpha 1, alpha 2, etc. We are, for some reason, severely interested what representation will have this vector phi in another basis, say S, with vectors S1, S2, etc. Let's represent phi as a sum of its components multiplied by the vectors of the basis E. Inside this sum, we can place the identity operator, since identity changes nothing. And as we remember, the identity operator can be substituted by the sum of projection to some orthonormal basis. Here I choose the basis S. This last step is justified by the closure relation we discussed in the previous video. If you carefully observe this expression, you will find out that there's no more vectors of the basis E in it. They got into the scalar products and they contribute to the scalar coefficients. The only vectors that remain vectors are those of the basis S. It looks good, but we are going to rewrite it even better and represent the whole thing as a column vector, but now in the basis S. This expression is still not good enough, so I decide to decompose it a bit more and represent it as a matrix multiplication of this nice-looking matrix and the initial vector phi. You can check that I did everything right by going backwards in this reasoning. You multiply this matrix by the column phi, and you obtain the column vector from above, which is the matrix representation of the expression above, etc. Good. Now, why we did all that? Because now I have the convenient way of representing any vector in the basis S. If I have some column representation of some vector in the basis E, I can just apply this matrix and obtain the column representation in the basis S. So this matrix is my basis change matrix. I will use the capital U to denote it. Now, what if we want to do a reverse operation? Suppose we have our vector psi in the S representation, and we want to obtain the components of psi in the E representation. Let's assume we forgot them. Since we have this basis conversion matrix, it is really easy to do. But before applying it to vector psi, we need first to calculate its adjoint. That is, to transpose it and to conjugate its components. If you do so, you may notice that U star, the adjoint of U, is also its reverse. If you multiply U star by U from left to right, doesn't matter, you obtain the identity operator. It means that U star conceals the action of U, as well as U conceals the action of U star. And if we applied U to some vector to obtain its representation in the basis S, then U star reverses this operation, and we obtain the initial representation E. The operators whose adjoint also is reverse are called unitary operators. As we just discovered, they transform an orthonormal basis to orthonormal basis. They also don't change the length of vectors, and they preserve angles. Good examples of such operators are rotations and reflections. Now, important point about this type of operators is this. Any evolution of a quantum system, except for the measurement, is described by a unitary operator. It means that when we are going to perform computations on our quantum states, that is, to modify them, we are only allowed to perform unitary transforms. We cannot apply just any linear operator we want. All quantum gates we can implement are unitary. This is quite a strong restriction. Sometimes there is a very strong desire to implement some gate which is not unitary. For example, to copy an unknown quantum state, but we just can't. It is the fundamental law, and we cannot break it, no matter how we want it. Physically, this restriction means that one cannot distinguish the evolution of a quantum system from evolution of its environment. Basis change, and it is what the system does when it evolves, can be performed outside of the system. For example, if we consider the qubit encoded by a photon polarization, then it does not matter whether we rotate the photon polarization axis by angle theta, or we rotate our analyzer by angle minus theta. The result of both these actions is the same. Now, what about the quantum gates we met before in the previous episode? Can we use them in quantum computing? Are they unitary? Yes, they are. You can easily check it yourselves by computing the adjoints and performing some matrix multiplications. You may even remember that all these quantum gates are self-adjoint. But I don't want to steal your pleasure of doing this exercise. Instead of that, I want to introduce you one more unitary Hermitian operator. People know it by different names. Some call it CX, some conditional not, and we are going to call it C naught. As always, this new operator is extremely important. In this course, I don't even mention unimportant things. First of all, it has matrix 4 by 4, which means that it acts in the state space of 2 qubits. And second, it modifies the value of the second qubit based on the value of the first qubit. It flips qubit 2 only if qubit 1 is in the state 1. I remember that I already mentioned this operator when I explained you why we need the entanglement operators, or operators which in some sense make qubits interact. Without these kind of unitary transforms, we can only perform the trivial computations. So this quantum gate is our gate to the world of almost unlimited computing power. And unfortunately, this is the gate whose physical implementation remains the most challenging task for physicists and engineers nowadays. So, as an exercise, check its unitarity. And if you want more exercises, find its eigenvalues and eigenvectors. And enough for this week. Goodbye.